So this is the 2012 Scholarship Physics paper question 4, and we're looking at motion. So there's going to be lots of energy and momentum, that kind of stuff. Ball X is released from rest at a height h, hits the ground with a speed v meters per second at precisely the same time as ball X is dropped. At precisely the same time as ball X is dropped, y is launched straight up from the ground at v meters per second. Straight away, before even looking at the questions, we've got a bit of a setup we should draw. We've got ball X that's dropping down, and it hits the ground at a velocity of v meters per second, starts with 0, and we've got another one which is ball Y, which is launched up from the ground at velocity v and hits the top at 0 velocity. Travels a distance, both travel a distance of h. And so what we've got here are two exactly identical paths. The only difference is one runs in reverse with respect to the other. So they're exactly identical. So there's possibly going to be some symmetry things we can use to help our questions and answers. Okay, A, show that the two balls will pass each other at a point 1/4 h from the release point of ball X. So from the top, we're looking to find a distance that is 1/4 h. I'm just going to call that x, and we're going to call the bottom section y. So x just deals with what we're looking for, so we're trying to find x, and y is going to be something that we'll use just to do some equations and things. But anyway, so we're showing the two parts. Now, a very important thing to note with this is using that symmetry idea. When the two balls pass each other, they'll be at the same velocity. Okay, we'll just call that VF, final velocity. So they'll both be at the same final velocity when they pass each other because of the symmetry. The same amount of time will have passed for both. So one will have been accelerating under gravity, one will have been decelerating under gravity for the same amount of time. So they have to have the same velocity, which would be meeting in the middle from where they were. It'll be the half the velocity, v over 2, I think even. You can explore that one yourself, it's not necessary for this question. So what we're after is a distance, x. So if we were to give you a formula for the distance x, it would be using the kinematic equation d equals vit plus half at squared. X is going to be, because vi, if you're taking the x but dropping, then the x ball dropping starts at 0 velocity, so vit term goes to 0, so it's half g, which is our acceleration, t squared, except when we're dealing with the entire journey down to the ground, that's a full t, so this is going to be t by 2. Okay, this is going to be t by 2, so t over 2 squared. So that's one useful equation. We can do the same thing for y. Oh no, we can't do the same thing for y, that's the problem, because when it's dropping from y down, it's going to give us a different, like our initial velocity is not 0, so it's going to make it awkward. We could do it in the reverse, going up for ball x to give us the distance y, but we don't actually need to. We can do it for the whole time h, or the whole distance h for the whole time. Ball x dropping, half, exactly the same except half g, this time it's the full t squared. Okay, so now we've got two terms and two parts that are in terms of t squared and g. We could expand out the x term to make it half g t squared over 4. So we've squared the t and we've squared the 4. And if we wanted to take this a step further, we could put x in terms of h, which is what we're trying to get straight away. And you can see from this already that there's a component of x at half gt squared, which is the h part, half gt squared. So from that we can show that x equals 1/4 times h, which I guess is what we were trying to get to. That's a much more elegant solution than the big long one I had prepared. So there you go, that's nice. You can get into tricky other ways of doing it. That's a third way I've seen that done, but that's the shortest as well. Use physical principles. B. Use physical principles to explain this result. This is a little bit of a vague question, so how I've approached it, and also with the benefit of hindsight to look at the marking schedule, is I've just described the motion of ball X and the motion of ball Y. So if I read it to you, I would say, or I'll try it this way: X is accelerating under gravity downwards from initial velocity of 0, and accelerating under gravity, and we would say perhaps at half the time, half t, it's accelerated to a particular velocity, final velocity, which we would maybe assume might be half of v. I have to think that one through a bit more, but that's not necessary for this. And the distance covered has to be less than half of h, because it's still accelerating. So the second half of the journey, for the second half of the time, it's going to cover a greater distance, so it has to have only covered less than half of h. And it's still speeding up, yes. So then you would say pretty much the same thing for y. You would say it's accelerating under gravity downwards, but it starts at the initial velocity of v upwards. At half the time it's going to be have covered more than half the distance, and it's decelerating still, and I'll reach 0 at the top. And you might like to say that both paths are symmetrical, just about the time axes, if you like. So anyway, moving on. C. A ball of mass, in fact let's just move this up, top of there, makes it easy to search through if you're trying to search through for a question. You see it moves to the top of the thing. Okay, a ball of mass m makes a head-on elastic collision. That's important. So if it's elastic, it's going to be conservation of energy, kinetic energy. The stationary second ball of mass m and rebounds with a speed equal to 1/3 its original speed. Show that the mass of the second ball is equal to 2m. The solution for this is to have two equations. There are two things conserved. And one of those is kinetic energy, so we can write an equation for the kinetic energy, and the other one is momentum. We can write an equation for the momentum. For a convention for this, it's easier to draw capital M for the big mass m. Oh, it says it already. And small m for the small mass, and big V for the velocity of the big mass, and small v for the velocity of the small v. So initially we've got small m little v as our initial momentum. Then afterwards we've got capital M and capital V momentum plus 1/3 small m small v. So that's one equation. It's one equation with 1, 2, 3, 4 unknowns. But remember, we don't have to worry about getting rid of one of these unknowns, because in fact we don't even need to worry about getting rid of two of the unknowns, because we're trying to find capital M. I'll just put this as a goal. You should perhaps write down your goal when you're doing this so that it helps you aim for it. We're trying to show that capital M equals 2 small m. So that's what we're aiming for. So we're only eliminating the V's. Second equation, the kinetic energy equation, and then I'll leave it there and you can work it through yourself to solve it. You've got initially half small m small v squared. That should equal half capital M capital V squared plus, I'm going to run out of space so I'll draw it underneath, what have we got? It's half m, because it's still the small mass, but the velocity has gone to just 1/3. Okay, so v over 3 in brackets squared. So remember, the squared squares the v as well as the third, so it'll be half mv squared over 9. Okay, so as we said before, we're trying to eliminate the v's. So what would make sense would be to rearrange the top formula, okay, to get it in terms of capital V squared, or just capital V, which we can do without too much trouble. That would be small m small v, we're not doing squareds, minus small m small v over 3, and then all of that divided by capital M. So I'll just divide by capital M. So then you would substitute that in. You would take all of that and you would put that into this one here, and then you'd just rearrange and your V's would hopefully cancel out. In fact they do, and then you'd be left with just M, capital M equals 2M. So I'll leave that for you to work through. That's the trick. Okay.